So previously, we used to measure the spread of infectious disease with this kind of model, thinking that everybody mixes with everybody, okay? So everybody is just as likely to become infected than anybody else. It's not true, because in reality, we make social networks. So if this person is infected and I'm here, I can just relax for a while, because that thing is not going to come to me until it makes its way all the way around like this or all the way around like this, okay? So we must understand social networks, how complex they are, what style they are, if we want to understand how things spread, information but also disease. So back to Japanese macaques. As a complex primate, they form complex social networks. This is a social network from Koshima in Miyazaki. This is a social network from Yakushima. They look almost the same, with one big difference, and it's here. Modularity means how much substructure, how many subgroups are there in the network. In the Yakushima forest, there are many more subgroups than Koshima. They have a higher modularity. So what does it mean? In Koshima, those high-ranking female spreads disease really quickly to all of her partners. This is just computer simulation. Low-ranking females, not so much, all right? That's, as I said before, social centrality, faster spread, faster getting sick. But in Yakushima, so this is a complicated graph, I realize, but here's what I want you to do. Think about the blue line, and if the blue line looks the same or different than the red line. Here, the blue line is increasing in all cases. That means if you're central, you are spreading disease to more individuals and you're getting sick faster, okay? But that's in Koshima. In Yakushima, the blue line here for getting an infection is the same as the red line. The red line is random. So the Yakushima social network it's behaving more random than the Koshima network. And it's probably because those monkeys subgroup a lot more. Yakushima is very big. Koshima is very small, all right? And so the type of network determines how those infections spread through the network. So if we understand what the network looks like, it can help us predict what will happen if an outbreak happens in humans or in animals, in nature. And if it's really bad, like Ebola in chimpanzees, some people even think, if we know the network, we can pick the very central chimpanzees, usually males, and we can vaccinate them with some drug to stop the spread of Ebola, okay? And that's for conservation, to save those animals in the wild. So understanding how complex the networks are really helps us understand these complex patterns. And so just to show one last time here, these are three different types of networks: connected, modular, star. And if you simulate disease, in 100% of the cases, more individuals get infected in this model than in this model, okay? Because subgroups slow down infection. It slows down infection. So with a few collaborators, another graduate student, Valeria Romano, who's defending her PhD next Friday, we developed a model. It's a theoretical model because we're interested in the trade-off. Individual behavior, and they interact with each other. They make edges, links between other individuals. They build a social network. They can get information, but they also get parasites. How do they balance those two things? Our model looks like this. It's a bit complicated, but these are all the different possibilities, okay? Orange is how much information they have. Blue is how much disease they have. If you're connected to a friend that has a lot of information, it's great for you. But if they're always sick, it's not good for you, okay? So how do you build a social network from that? So the last activity I have is really about four examples, okay? My question, so here, information, a lot of information, no disease. A lot of disease, zero disease, no change in information. A lot of disease, no information, and it's the same. Which network will give you the star? Okay? The star is only one individual at the center of the network, okay? You can think about it. I'll give you the answer in a second. It's not this one, because nobody is sick. So all of the individuals can interact with each other. It's not really this one, because some individuals are sick, others are not, but everybody has the same information. So there's still value in connecting with those individuals. But it's actually this one, because nobody has information, right? And there's some disease in the population, so they pick one individual with no disease and they completely interact with that individual, all right? And here's more or less a full network with that condition. So we're trying to understand how networks evolve with these conditions. And with that, I just want to finish my talk. Two different aspects of organization and behavior and how we use complexity to understand ecology on those systems.